Good morning, good morning. Good mathematical morning. I'm basically just popping in to say a quick hey. Probably shouldn't even stream this morning because I got a tutorial I need to prepare for. But I thought I'd come say hey. And talk about some random stuff. Yeah. Oh, I've been forgetting to like my own videos. And then also, yeah, I guess normally I would have started streaming by now, but I got carried away doing math, which is a good thing. That's what I should be doing, is prioritizing my thesis writing in the morning. So I don't know, maybe we'll go to Reddit. Oh, Christopher Havens has a new paper. I used to volunteer with the Prison Math Project. By the way, yeah. Good morning, quality content. Good morning. Let's see. Continued fraction. Right, I remember he was working on that stuff. I had some chats with him over the phone back in the day. Cool. Cool stuff. Yeah. Submitted 2020. Oh, so this is old news. Because I knew he had submitted something a while ago. Oh, yeah. Okay. Oh, I thought maybe this was a newer publication. Still good to see. I guess maybe this is just people discovering his stuff. You've got office hours on a projector at the small REU. What's the small REU? You mean a small REU? Are you guys you're doing like a summer research thing and you're all working together in the office? That's pretty sweet. I should maybe hundreds of you. That's wild. I was only gonna have I need to have a short episode today. I wasn't gonna. There's no way that's actually true. But or is it? I don't know. I wasn't planning on yapping on anything too substantial today, and I have to go because I have a lecture for thousands. Even could one even say it's tens of thousands? I should dig up somewhere some pictures. I fondly remember the REU I did in my undergrad, and there was 3 or 4 of us that just hung out in the same room all day and worked on worked on our math all day, and it was fun. It was a lot of fun. Did I see Hannah Cairo's paper? No. Refutes a mathematical conjecture. So-called harmonic analysis. Damn. Crazy. Yeah, let's find. Where's the actual paper? Let's go to the paper. Wow, and it's even posted as a single author. Crazy. LP estimates of the X-ray transform of positive measures in RD. That is some wild stuff. Well, definitely we'll be looking forward to hearing about her crazy career and what comes out of it for sure. Oh, it has to do with the Kakaya conjecture. I don't know the right way to say that. Wow, very cool stuff. Yeah, maybe I should spend more time. I think previously I was doing some trolling through on archive. Oh, you can see I was looking at this one already yesterday. I think the answer that they talk about in whatever this book from the Warhammer 40K. I thought it was gonna be. I was kind of hoping when I saw the title of the post, it was gonna be like an interesting math problem that had to do with actual gameplay, like they were trying to work out the statistics of some dice rolls or something. But 119 is sort of the largest cyclic subgroup. So maybe this name is just invented, and they might have just meant the monster group. Someone in the comments below pointed out that the monster group has order 119, so it's probably a reference to that. Yeah, undoubtedly. Yeah. Yeah, interesting. Yeah, do I actually have some in my very short and limited office hours? Do I actually have some mathematics content to talk to you guys about? The original quote is "Grad students can't be fired." Huh? You mean the Warhammer thing? Something about grad students can't be fired? Sorry, I don't understand. Where was I in demodule land? Maybe we can say something there. Right. So maybe I'll say something about the Riemann-Hilbert correspondence. Because so far my work has largely involved perverse sheaves. And so what are those? Well, let's just take the most basic definition that's not even a real definition. It's a complex. It's a special complex of sheaves. So, ... It's just a complex of sheaves. And where I should say, which is bounded according to numbers coming from dimensions of strata. So, we've got some stratified space, like a union of orbits or something. As roughly strata, well, and like support of the sheaves. So, for example, if you have your perverse sheaves, if you have some smooth variety, your perverse sheaves are just going to be the local systems in the degree of your variety, right? So it'll just be a complex basically where you just have a local system sitting in the degree of the dimension of your variety and nothing anywhere else, right? So the point is that if this is not concentrated in a single degree, then it's detecting the presence of singularities. And, well, so I guess actually it gets maybe a little more sophisticated because I guess what I've said is maybe a little bit wrong, but the idea is we're going to work with, like, so we're working, like, this should be a complex in the constructible derived category. And in particular, we want to look at sheaves that are constructible with respect to our orbit stratification. And if we have orbits whose closure is not smooth, this will manifest in the perverse sheaves that we're interested in having, like, it will create non-trivial entries in some of the other components. Yeah. So, oh, Hobster's in the chat. Hobster, true number one fan for life, despite what the rankings in the chat say. Yeah. So this is the focus of my research. Well, and I think I said yesterday, I talked about, Kasdan-Lustig, and ultimately we're relating representations of some group. I mean, for me, instead of a complex group, it'll be p-adic. Instead of this variety, will be actually an easier variety to understand. And the key step is passing through the Riemann-Hilbert correspondence. And actually, why I've been studying D modules lately is that I'm hoping by going back and forth between these two, I'll be able to use computational tools from D modules to better understand it. And so, in particular, I mean, there's some more fancy words here, but that I haven't explained. So there's the category of D modules. But not only are they D modules, they have to be what are called regular holonomic D modules. Don't worry, we're not going to talk about that today. And the point is that there's an equivalence of categories from the regular holonomic D modules to the perverse sheaves. And this is all very fancy, but actually we can compute this very explicitly. So why don't we go through this computation using the determination from the other day. So remember, what did we do the other day? So we took we had, again, the complex numbers, again, stratified into this union of orbits. And we looked at the example of the structure sheaf with the exterior derivative as a quasi-coherent sheaf with flat connection, which then determined a D module and D module M. And we looked at the minimal extension, which we used the axiomatic characterization of to conclude that the minimal extension was the same as taking, so if I write X for C, I'll write it like this, was taking this quotient D module. And so now what we might do is plug this quotient D module into the Riemann-Hilbert correspondence and see what we get out. And okay, definitely on older previous videos, I think I already computed the perverse sheaves in this example. Maybe I'll recompute them just to see that it coincides with what we think it should. So, but basically, it turns out that we have a very explicit way to compute the Riemann-Hilbert correspondence. So what does it do, the Riemann-Hilbert correspondence? Well, it supposes that you have a D module M, and you feed in that D module, and you should get out a complex of sheaves. Okay, and so again, we've neglected the formal definition of a perverse sheaf. You know, this famous theorem. You know, you got to go do the work to check that you get the special kind of complex out. But we can at least plug the machinery in and do this computation. And so one way to do this is to take in particular, the Riemann-Hilbert correspondence says there's a particular functor called the de Rham functor that realizes this. And so we could apply the de Rham functor to M. And there's a theorem that says, well, so that's some complex. If you shift it into minus the dimension of n, that complex will be given by the following. So you take your D module and you tensor with the zero forms, and then you take your D module and you tensor with the one forms, and you keep going, of course, until you tensor by the D forms. And then, of course, you know, this sequence keeps going forever, but it's zero in all of the other terms. And what are the differentials of the sequence? Well, it's just going to be, so dm alpha will be, so I guess if we're taking local coordinates, hello, Mr. L. Hello, Mr. L. Actually, I gotta cheat and look up the actual formula. I've got too many tabs open. Here we go. Yeah, so if we know what our connection is, okay, there's a different way to define this, but so if you know what your connection is, we can so if M, you know, is a quasi-coherent sheaf together with a connection, we can define this as nabla acting on M tensored with alpha plus yeah, let me check. S first, so M in this case, wedge D alpha. M wedge D alpha. Okay, so we can actually do this computation, right? Because in this case, so what is our de Rham of this D module? Well, we know that if we shift, we're just on the complex numbers, so it's dimension 1. So this just becomes this, Yeah, I guess the more general way of saying this. Hang on, I've got a better way of writing this in overleaf. Oh, actually, I need to go. It's 9:05. I gotta go teach these kids, man. I gotta go teach these kids about how to prove things. That's what they're paying me for. I hope you guys appreciate my mouth music. Here we go. Yeah, d omega, and then, right. This is the better way to say it, I guess. Oh, I put the tensors on the other side. That's not a problem, but... Shapira's notes? No, is not Shapira's notes. The overleaf are my notes, of course. These are Peter Eatonof's notes. Pavel Eatonov. Yeah. So yeah, let me just write down the more general way, and then I'll leave it as an exercise for all of you guys to. Oh, you studied categories with him. Nice. Wait, with Shapira or with Pavel? So maybe I'll just say, let me like make a correction, and then I'll let you guys do this as homework, and then tomorrow I'll give you the answer. But so the differential can actually be given like this. You don't need to know the connection. I mean, again, a D module is equivalent to a quasi-coherent sheaf with connection. But the other way to write the differential. Wow, that's awesome. Studying with Shapira. That's pretty sweet. How was the course? What did you guys do? So dm alpha. So in this case, I mean like this d is going to be the differential, and we use a different d for the exterior derivative. So choosing local coordinates, giving us a system of xi's and del xi's. We take the first thing will just be tensoring with d alpha. Terse and minimalistic style. I mean, I wonder, yeah, maybe that doesn't make for the best learning environment. But then again, I mean, if you're dealing with a Giga Chad at the level of Shapira, maybe that's what you want, right? Because, like, to get the most out of him, I mean, I don't know, maybe you have a different opinion having gone through it, but if you want to get the most out of his abilities, right, you probably want him to talk about, like, the cutting edge and the big ideas and the way that he views things, right? Whereas, like, you can find someone else to give you a pedagogically sound, handheld version of the course. But, I don't know, maybe I would feel differently if, like, my grades were on the line in that course or something. Interesting that he hates spectral sequences. Yeah, aren't they, like, the most amazing tool? I don't know. I've never totally got my head around some spectral sequences. I've done some reading. I need to do more exercises to make sure, yeah. Anyways, let me just finish writing this differential. So you can see, I mean, this term I'm writing here basically is the connection term. It's how the connection acts, but you take the this is basically the connection term, but it's written more just in a purely D module way. You just take the action of the differentials locally, and then you wedge by dxi on the left. And so in our we just have a two-term sequence, right? We have this tensor with our structure sheaf. And then this tensored with our one forms. And then that's it. So really, we just want to, and this is our diram of this D module shifted by -1. And so we just need to see, we just need to, compute this. So we already know that this whole thing is the kernel. So what is this whole term going to be here? Well, I mean, this is basically just OC, right? And then tensoring with OC. So basically this is just OC, right? Which is, wait a second. And what is what I'm saying true? Because we should be getting the constant sheaf out of this. We should be getting the constant sheaf out of this. Oh, right. This is the complex. This is just the complex, and we need to take the cohomology. Yeah. But wait, the cohomology should just, right, the cohomology here should just be the kernel. Okay. I didn't pick up on your JoJo reference last time. Yes, because I've never seen that show. So would not be possible for me to do that. Okay, so maybe actually this is a good time. Okay, I really do need to go. I can't stop yapping though. So maybe I should say the following: computing perverse sheaves explicitly is hard. I will give you some examples where we compute it explicitly, but often. So often what we mean by computing a perverse sheaf actually just means, given a perverse sheaf, compute the cohomology of that sequence and its restriction to each of the orbits. Yes, Collar differentials. Those are Collar differentials. So normally that's all we mean. So we don't necessarily need or want a totally explicit description of the complex defining the perverse sheaf. Rather, we're happy to just compute each of the cohomologies, and we know, right, this is just going to be some sum of local systems on the orbit, and so we just want to see what local systems show up in there, and that for us is often sufficient. Yeah, maybe I'm not going to give the definition of perverse sheaves probably for a couple office hours. It's sort of, I don't know, we always joke that it's the way that we have learned it in our group is the engineer's perspective, right? So like the way that an engineer learns to do calculus. You learn to do integrals and derivatives, but you never learn the like proper definition. You just sort of learn these rules, you understand how it works, and then you go and learn the definition. And honestly, I feel like this is the better way to learn it. Because, like, I don't know, the definition's not very enlightening. in my opinion. So it's better to just learn these computational tricks about how to do these computations, and then later learn the definition. And then again, like, it doesn't matter. I've never appealed to the definition. No, that's not true. I shouldn't say never, but like, yeah. That's not true in Europe, you're afraid. Yeah. Well, I think when it comes to calculus, the Europeans do it better. I think the European way is the right way. But I think when it comes to reverse sheaves, the American way is the right way. Okay, anyways, I'm going to go for real. These kids need some learning. So I'll see y'all soon. Go prove some stuff.